by the security alert here. There we go. Thank you all for being here. It's a pleasure to be invited to Oklahoma City and see such a great turnout. I'm the presenter today. I'm the talking head for the research, but just remind you that this isn't just Dan. This is a collaboration, as Dean curtly indicated, working with NIST, working with Underwriters Laboratory, working with fire departments across the country, working with universities across the country. University of Maryland in the far east, University of Illinois. We've had students from Oklahoma State University as summer students working at NIST, and as far to California with Cal Poly. So it's really been a big effort to be collecting this data over decades. It's not something that just happened or that was done with a couple of fire tests in a city and we said, you know what, Holy Grail, we're good to go. This is a body of knowledge that's been developed over several decades, and it's a relatively new body of knowledge in terms of fire dynamics. The first textbook on fire dynamics wasn't published until the mid-1980s, and that textbook was really aimed at engineers and scientists trying to set a foundation. And then the Society of Fire Protection Engineers came out with a Fire Protection Engineering Handbook that's currently going to have a new edition here in 2015. But again, laying the baseline, the groundwork for the understanding of fire behavior and the interaction with structures and people. So what we want to do today is give you a little bit of background. My task this morning is sort of discuss your working environment. Where do you go to work? And we also want to talk a little bit about how the fire dynamics then interact with where you go to work, that residential house fire. I want to talk to you a little bit about your PPE. How much do you know about it? You're certainly trained on how to don it and doff it very quickly. Everybody's sitting there with stopwatches and all that sort of stuff, but what will it really protect you from? Do you have a good idea? Based on the blogs that I see on various web pages, it would appear that at least the firefighters that are sitting there working the blogs don't have a good idea of what their gear can take. We hear things like, oh yeah, I've got to be in 1,000 degrees before my face piece is going to melt. False, right? So make sure you understand what your gear will do for you. Don't push it past its limits. And then that gets us to some tactics. The importance of size up. If you don't size up before you go in, that's like strike one. If you don't identify where the fire is before you go in, potentially that's strike two. Some people refer to this as sort of a Swiss cheese effect, that eventually there's so many holes in what you're doing that it lines up and results in a tragedy. Maybe a serious injury to one of your firefighters, or maybe a line of duty death. It's never just one thing that's gone wrong. It's always a series of things, a breakdown of what needs to happen to appropriately attack that fire, safely and effectively attack that fire. So size up is step one. And then we hope that from what you hear today, you'll say, now that I have an understanding of where that fire is, how involved that building is, what the situation is with regard to rescue, is anybody viable in that building or not, you'll be able to choose some tactics that fit that specific fire, as opposed to running out there with a one-size-fits-all mentality, right? That's how people get in trouble. The federal government has invested a lot of money in NIOSH's research into how firefighters die. And you don't have to review too many articles to start to see certain trends, right? There's no size up, lack of communication, all these sorts of things. It has nothing to do with fire dynamics, but it does. Because the basics of fire dynamics is something that every firefighter had in Firefighter 1, and that's the fire triangle, right? You need fuel, you need heat, and you need some oxygen to have a fire. The problem is nobody connected the dots in many cases to get you to apply that fire triangle when you're looking at a structure fire and say, what does that fire need? Now, some of the greats, like Chief Vince Dunn from FDNY, he's one of those guys that's made that connection over the years. There have been many others. Guys that write in the magazines and write textbooks and whatnot, that's what they're doing. We're trying to help you guys do the same thing. So most importantly, let you fight that fire better. Get it out faster, get it out more efficiently. That will improve the safety of you and your crew, and that will give you the best chance, if there's a viable victim, to rescue them. We want to give you this information. This is streaming. This is going to be on the FSTAR website. The presentations you see today will also be loaded on the FSTAR website so you can access them. And hopefully you'll take this information back to your departments and work with it. Hopefully this is not news to anyone, that your workplace has changed. And since the census started keeping track of this data in 1973, the average house size in the United States was 1,600 square feet. In 2008, it's up to 2,500 square feet. So homes on average are getting quite a bit larger. The housing lots, as you see in the next line down, are getting quite a bit smaller. So we have homes closer together. What does this result in? This results in fire departments in suburban communities responding to fires, and by the time they arrive, by the time they're called, there are 3 or 4 houses involved. By the time they can stop it, maybe 9 houses are damaged. This is going back 100 years ago, right? Before the building codes, when we were worried about losing portions of cities. Now we're losing portions of complexes. Earlier this spring, there were a number of fires of buildings under construction. I guess the first day of the week, they had a multi-million-dollar loss in San Francisco. Later, they had, I believe, a $51 million loss in Houston. I think probably everybody saw the video of the worker that was stuck on the balcony and made the leap of faith to get on the ladder truck. And the next day, they had a $15 million loss in Montgomery County, Maryland. Right? Pretty aggressive fires. The buildings were almost done, but not quite. They were going to rely on a sprinkler system to protect the occupants, but the buildings themselves are made of what? Made of wood. There's trade-offs. We're going to put sprinklers in to protect the occupants when they're done, but in the meantime, we're going to make the buildings bigger, allow you to put the buildings closer together. Maybe you don't need to worry about collapse room for the fire service. Maybe you don't need to worry about whether or not that fire apparatus can turn around in that development, because the sprinkler is going to save the day. Well, in most cases, it certainly will. Excellent technology, fantastic. But if you get a fire up in an unsprinklered attic, starting from the outside working its way in, which we're seeing quite a pattern of today, or if you get a fire while the building's under construction, it's quite a sight to see, and I'll show you a picture of one of those here shortly. During the past 50 years, fuel loads have changed dramatically. 50 years ago, if you wanted to buy a sofa, more than likely you were going to have some choices. You might be able to get a seat cushion in your sofa that had metal springs in it. It had cotton batting around it. If you picked it up, it weighed about 4 pounds. Or there may have been some sort of synthetic material, some kind of rubber or synthetic rubber, foam rubber type material that you might have had in your sofa that was still pretty heavy and dense. And over time, polyurethane foam basically was perfected for residential use. So if you go to pick up a couch cushion today, in many cases it's going to weigh about 1 pound. So it's lower density. Its surface to mass ratio has changed. Again, stuff that you guys learned in Firefighter 1. And what that means is it can ignite easier and it can burn faster. And not only that, the heat of combustion of that material, the amount of energy per pound, has gone up by a factor of 2, in some cases a factor of 3, compared to the old cellulosic materials, wood, cardboard, wool, things like that. So there's a lot more energy in people's homes today, stored energy in people's homes, and it takes the form of carpeting, furniture, and other interior finishes. That results in fuel-rich conditions in the home, very different conditions than you might have had if you made a fire call in the late 1960s. The home designs themselves, as you can see from the bottom 2 images, have changed quite a bit. In my neck of the woods on the East Coast, if you're going to buy a house in the Washington, D.C. area in the late 50s, early 60s, more than likely it was going to be a 1-story brick rancher. There might have been a few 2-story brick colonials, but most of them were brick ranchers. Had a basement. You could tell it's pretty simple design. 1,200 square feet, 1,600 square feet would be a big one. Notice how flat the roof is. Notice how simple the roof geometry is. Notice how small the windows are compared to the windows in this housing model of, say, 2005. The other issue is they're using dimensional lumber in this structure. And what that does is limits the size of the room that you can have, because the dimensional lumber can only span, say, depending on the size, 12 feet, maybe up to 16 feet. So the house sizes between the area between bearing walls, load-bearing walls in this structure are probably going to be 16 feet apart or less. If you've got a 12 by 16 foot room in that house, that's a big room in that house. In this modern house, that's not the scenario at all, right? We can now use trusses, engineered lumber, which have great advantages because they can give you a more open environment. So if mom's cooking in the back room, she can look over and see dad working on the computer in the den, or see what the kids are doing in the family room on the 60-inch television that they're watching, right? They could go 40 feet, front to back of the house. Great stuff. In this particular house, in many homes, you'll see an open foyer or a 2-story great room. Where does smoke flow? The path of least resistance. There's hardly any compartmentation in this house compared to this house in terms of smoke movement and energy movement. So there's less compartmentation, and that less compartmentation is brought to us by engineered lumber. And engineered lumber is great. It's less likely to warp. You can tie your floor down to it better. It's less likely to squeak and all that. However, it's lost some mass, and as a result, it can heat up quicker. When it's exposed to fire, it can lose its structural integrity much faster than a solid piece of dimensional lumber. So it's covered with gypsum board. So that's a protection. You want to keep that gypsum board in place. Parts of the home, however, don't have that luxury. The attic, typically, the wood's not protected, and in many parts of the country, the basement structure is not protected either, so the wood is exposed. It'll get involved in the fire much faster. The homes are energy efficient. I mean, they're literally wrapped in plastic, right? We want to make good use of our energy resources, right? Be good conservators of nature, as well as save some money on our electric bill. The way we do that is insulate the house. What does that mean for a firefighter? That means that there's not as much leakage in these houses, either for smoke to get out or air to get in. So you're arriving, if the occupants don't leave the door open, or if the fire hasn't self-vented a window, you're arriving to a very different condition where this home, this basically a cooler, well-insulated cooler, has been storing gaseous fuel waiting for you to get there. And then we'll see how that reacts. The thermal pane windows are less likely to break due to the energy from the fire. They take more energy to auto vent. So there's a lot of changes. Alternate energy sources, solar panels. We're hearing more about hydrogen fuel cells that are going to be used in cars, hybrid cars in garages, things like that. All sorts of differences. So the real question, bottom line here, is how many of your departments have staffed up and done a lot of training to change their tactics to deal with these changes over the past 50 years? Not many, right? If anything, staffing's going down. Resources for training are getting less. That's not the right equation. The good news, there's some good news in all this, right? There are fewer fires. Since the 1970s, the number of residential structure fires has gone down by more than 50%. The number of civilian fatalities has gone down by more than 50%. The bad news for the fire service is if there's fewer fires to go to, you're getting less experience. So again, you need some training to replace that experience. But in many cities, there's not a budget for training, or in many cities, they don't have a facility to do live fire training and have to rely on neighboring jurisdictions either to use their training academy, or if there's an acquired structure that they can all get together and work on. Equipment and building standards are working to catch up with these advances in technology. The types of insulation that people are using, the types of materials that people are using in buildings are changing very, very quickly. And so the codes are working to keep up with that. Unfortunately, in many cases, what drives the code change is after there's been a firefighter fatality. And there's currently no national standard on firefighting tactics. And in part, that's due to some belief that a fire in New York is very different than a fire in Chicago. The physics are the same. And then we have this disturbing reality which is driving our research at NIST. According to the NFPA, the traumatic fires on the fire ground have almost doubled in the same period of time where the number of fires have been cut in half. This is absolutely the wrong trend. Another trend that we're seeing is that the property loss and the cost of fire in the United States continues to increase, even though the number of fires have been cut in half. What's going on? Something's not working. And again, with this decrease in the number of structure fires, where are you going to get your knowledge? And so hopefully today is one of these places you'll get some of the knowledge. I'm going to do some brief refresher now as we get into the fire dynamics. Radiation heat transfer. It's heat transfer by light energy. If you're the firefighter crawling into this room, you're going to get some radiant energy directly from the chair, the flames coming off the chair, and you'll get a lesser amount of radiant energy coming down from the hot gases going over your head. Convection. This image shows when ventilation is working correctly. The fire is small enough that the hot gases are going out and over your head. The fire's acting like a pump. It's pulling in fresh, cool air over you, cooling you off, taking some of that radiant energy heat transfer away, and then taking the combustion products, which is basically adding mass to the surrounding air and adding energy to the surrounding air and toxic gases, and pumping them up and away under a higher pressure and out the door to a lower pressure area. So again, this is the good case. Now imagine if all of a sudden you're in that hot gas flow. Now instead of the fresh air coming in and cooling you off, you're going to get energy from the convected gases added to the energy from the radiant light energy, heating you up, reducing your safe time in your turnout gear. And then last but not least, we have conduction. And most people think about conduction as touching a hot surface, such as touching the floor. But think about how your turnout gear protects you. Your turnout gear is made of material that is a good insulator. So it absorbs energy and slows down the rate of heat transfer to your body. Well, the way it slows that flow down is it's absorbing that energy. It's holding it. It's storing it. At some point in time, that stored energy is going to transfer to you. In physics, heat always goes to the hot thing, always transfers energy to the cold thing. Hot always flows to cold every time. So when you're in the house fire, what's the coldest thing? Probably you. So the heat's coming in your direction unless you do something to reverse that. And this is our challenge. The gear is so good today that it absorbs quite a bit of energy before you really start to feel it. And in many cases, by the time you start to feel it, it has absorbed so much energy that the burn you're going to receive may be just coming from the stored energy in the gear itself. There have been many instances where the fire's out and a firefighter leaving the building brushes up into the door jamb and presses the hot turnout gear against his arm and has blisters on his arm from the stored energy. Or many of you may have experienced the blisters where the gear is compressed due to your straps from your SCBA. So stored energy in the gear and it's being conducted to you. This slide is a little dated, but it's the best we have, and we're working on collecting enough data to rebuild it. This is from the 1970s. And what you see on the left-hand slide here is air temperature. So in other words, convection heat transfer. And what we see on the bottom here is the rate of thermal energy transfer given in heat flux, or kilowatts per meter squared. This is the radiant energy transfer, and shows how they kind of add up together in the middle. So 1 kilowatt per meter squared is the amount of radiant energy you would get from sunshine on a beautiful cloudless sky in July or August. And then over here we have temperatures. the degrees F are on the inside. So we see that routine working conditions are at about 160 F and 1 to 2 kilowatts per meter squared according to this graph. So twice bright sunshine added to about 160 degrees Fahrenheit your gear will protect you, and basically here you're going to rely on how long your bottle lasts in terms of being in and working in that environment. So you may have 10 to 15 to 20 minutes in this kind of situation. Then we get into the ordinary situation, 160 to 400 degrees Fahrenheit and up to 12 kilowatts per meter squared. As we go from this corner to this corner, the amount of safe operational time that you have is going to be reduced pretty dramatically. Where down here we're sort of in this 10 to 15 minute range. Now up here we may only be into a 5 minute or less range. And again, it depends on how preheated you were when you got there, how tight your gear fits, and all sorts of other factors. Once we get into this emergency box, 400 degrees Fahrenheit and up and 12 kilowatts per meter squared and up, now you're less than a minute. You need to be moving. You're going to get hurt. Right? This emergency is just that. You cannot stay in those conditions without getting hurt. You need to be flowing water to cool the scenario off. You need to be closing the door to isolate yourself from the scenario, or you need to be able to get out of the structure, get out of that fire's path. One more thing. Granddad's fire. Back in the day, firefighters didn't have hoods. They had tin helmets. Some of them just had heavy farm coats and gloves to go in and fight a fire. And if you've heard any of those senior firefighters, what would they tell you is their alarm for getting out of a building? They're pointing to it, their ears, right? So if we think about it, anybody know what temperature your skin starts to blister? Around 135 degrees Fahrenheit or so. And so that's this fire, right? Those are these kind of conditions, the routine conditions that now with your turnout gear, you can stay in there for a longer period of time. When it started getting up here for Granddad, he's telling you it's time to leave. Wow. Big difference. And unfortunately, these differences have had consequences. Many firefighters across the country have paid the ultimate price because they were relying on a technology, not fully understanding what its limitations were. And as the NIOSH reports are collected, you start to see patterns. And in this particular instance, I'm going to talk to you about a pattern that we see with SCBA face pieces. Basically, these firefighters were all on air, believed to be on air when they died in the structure fire because their face piece melted out. So they didn't run out of air. They ran out of time because their face piece melted out. And the good news is NFPA and the manufacturers are all working to improve this situation. NIST has been, for the past number of years, melting many different kinds of face pieces and trying to help the manufacturers have a test method where they can determine what the conditions are. And what we've come up with is we need to expose the face pieces, especially the polycarbonate face pieces, are affected by radiant heat flux. Why? Well, they capture the wavelengths and store it. So you can have a situation where you are in 200-degree gas temperature, but you're in direct line of sight of a raging fire or a rollover, and it's transferring a tremendous amount of radiant heat flux to you. The polycarbonate is absorbing that energy to protect you, and so therefore inside your face piece it may only be 80 or 90 degrees with the air coming in from your SCBA, so you don't feel hot, but the face piece itself could be 400 degrees and melting because it's doing such a good job of protecting you as long as it can. And so what we see here is the time for it to get to about 280, which is the temperature at which polycarbonate starts to soften, it starts to lose its structural integrity. We call it the glass transition time temperature. And we see that if it's at 5 kilowatts per meter squared, you've got about 3 minutes to 6 minutes here, sort of looking at this rough span of these different face pieces. But as we increase the heat flux, you notice that all the data collapses to about 30 seconds plus or minus 10 seconds or so. So if you're being exposed to 15 kilowatts per meter squared, your face piece is going to soften within about 30 seconds. Let me show you what that looks like. Here I'm going to show you an experiment where I've got a gas burner 16 inches on a side. We're in a 12 by 12 room, 8-foot ceiling. I've got some mannequins here that we have on air. They have a mechanical lung, so they're drawing air out of an SCBA and breathing just as you would. And we're going to put a 500 kilowatt fire in front of them. So we've got a fire that's about 3 or 4 feet off the floor. If you were to walk up to it in your full turnout gear, that would look to you like an absolute nothing fire, right? So now you're in the mannequin's head. We've got a camera mounted in the head. You're looking out through the face piece. And we've got the fire going. So the face piece is being exposed initially to about 8 kilowatts per meter squared. And as the hot gas layer starts to develop in the room, even though we have an open doorway to the room, it's going to increase to about 10 kilowatts per meter squared. And at 3 minutes and 30 seconds here, you start to see damage already showing up on the face piece. And if you watch carefully, every time the mannequin takes a breath, you'll see the face piece move in and out, giving you an indication of just how soft that is. It's a little difficult to see, but we're going to shut the fire off in a minute. It'll be very clear that there's a hole opened up in this face piece already. The good news is, for the wearer of that face piece, is they're still being protected from the toxic gas environment because of the positive pressure maintained in the face piece. But you can see, this is real time, you can see with every breath the mannequin takes how soft that material is. Again, training. The worst thing the firefighter could do right now is try to wipe that. Because they pull it off their face or make that hole bigger, maybe the positive pressure can't be maintained. So NFPA came out with a new standard which has a test which addresses radiant heat flux, and now manufacturers are selling units that comply with that test, and I believe that many of them have a retrofit kit for your existing SCBAs. Should this have been a surprise? Not really. When you look at the test method that was in the old SCBA standard, they would put your SCBA in an oven at about 200 degrees Fahrenheit for 15 minutes. They have it on a breathing mannequin. They bring the mannequin out of this oven. The oven's about 5 or 6 feet on the side and almost 8 feet tall. And they expose it to an open flame for about 10 seconds. That is not a flashover exposure. That's a flash fire exposure. Very different things. And then they would bounce the mannequin 6 inches and make sure that the face piece stays on the mannequin and positive pressure is maintained. Well, if you look at what the electronic equipment is being tested to, they're starting to put it in convective ovens for 500 degrees for 5 minutes and make sure that it still works. Your turnout gear, 500 degrees for 5 minutes. There's a lot more energy this gear's being exposed to a lot more energy. And then, of course, you have your TPP test, which is a combination of convective and radiative flux, where they're exposing it to 84 kilowatts per meter squared. So is it a surprise that something that was really only exposed to 200 degrees might fail sooner than these materials? Why did they choose this? Polycarbonate can't take this. They'd have no SCBAs that could pass. Right? So now they're using new material or changing the design of the face pieces so they can now withstand this. And that's new for 2013. So again, keep in mind that about 130 degrees, human skin's got the potential for getting blistered, second-degree burn injury. Heat flux to bare skin at 5 kilowatts per meter squared, you're going to have pain to the skin in seconds. And when you're in a flashover simulator or you're seeing rollover in a structure, the floor is getting hit with about 20 kilowatts per meter squared. Once the flames are rolling over, you could be getting hit with anywhere from 60 to 200 kilowatts per meter squared, well above what your gear is tested to. And we continue to do work. Currently, it might surprise you, there's no thermal standard for firefighter radios. So NFPA is working to develop one, and NIST is working on developing the tests that they can use in that standard. And you see some of the examples here. We're looking at heat transfer through turnout gear to get a better understanding of that. And here, unfortunately, you see some melted handy-talkie mics and cords. Again, what's driving this? Firefighter fatalities. One particularly painful case in California for the people involved, 2 firefighter fatalities. They just bought a new radio system, heavily invested in a radio system marketed to the fire service as this is built heavy duty for you, day glow colors and all. This was not. This was the same specification as what they sell to the police officers or bass fishermen. The material here is rated to 140 degrees Fahrenheit. Did those firefighters know that's what they were taking into the building? That their safety line that they were taking, their communication capability was going to start to fail and break down once they got in an area that was over 140 degrees? Would they feel 140 degrees in their turnout gear? Probably not. So again, understanding what your gear can do is very important. Thermal imagers, fantastic devices, excellent devices, but you need to train with them. You need to understand what they can do and what they can't do. For example, a thermal imager is not an X-ray device. Most of the materials that we use in the construction of our home are great insulators. Plywood, oriented strand board, the foam we use under the carpeting. As a result, what does a thermal imager actually sense? They'll read out in temperatures, and we see some very low temperatures here. They're hard to see, but they're around 100 degrees Fahrenheit. What do they sense? Anybody know? They sense surface temperature? No. What do they sense? They sense heat flux. They sense energy. Thank you for helping me with the surface temperature. Perfect. They go through a calculation to give you an approximate surface temperature, but they can only see the energy that actually comes through that surface and is being emitted off that surface. They're assuming that it's a near ideal emitter. So they have an emissivity tuned to about 95%. A black body would give you a value of 1. Most things that you're going to encounter in the world are between 0.5 and 1. So you could be a factor of 2 off. So they're not a really good thermometer. And as you see here, this is the temperature on top of a piece of OSB, and this is the temperature on the bottom side of the piece of OSB. The fire's in the basement. These 2 thermocouples are less than 3/4 of an inch apart, and they don't really start to change dramatically until the structure's collapsing. So that thermal energy isn't going to be there for your thermal imager to see. So that, to make sure people understand that, you want to sweep the room, you want to look for air vents, you want to look for cracks or holes anywhere where heat may be coming up. And if you see a hot spot, what does that mean? What's the action to take? Stop. Right? Because what this test showed you was that you could be sitting on top of a floor that has lost its structural integrity and is getting ready to collapse and drop you into a post-flashover environment, and the temperature reading is only going to be about 100 degrees to 200 degrees Fahrenheit. Right? So keep in mind, you can't rely on the temperatures. You want to use that thermal device to look for movement, to look for contrast, to look for changes. Right? They're fantastic. Just make sure you know how to use the devices that you have in your department. So now we've been through the hard stuff. Let's start getting into some of the tactics, or some of the thoughts about tactics. Traditional tactics. I hear this a million times. This is how we've always done it. This is how we've always fought fire. And when you look in the older training manuals, when I'm saying older now, we're talking about IFSTA Essentials 5 and 4 and 3, it would say things like, whenever possible, attack from the unburned to the burned side. Ventilation was only discussed in a very positive manner, that if you ventilate, hot gases are going to go out, fresh air is going to get in, life's going to get better. So that was interpreted as vent to cool. The most effective and efficient fire attack is from the interior. Sometimes it might be, maybe not all the time. You want to attack basement fires from the interior. Go from the top down. And depending on what book you're reading, some of them may be a little emphatic, and they may go as far as like basically inferring, for the love of God, whatever you do, don't flow water from the outside. You're going to push fire. You're going to kill somebody. You're going to steam somebody. Well, let's start looking at some of these things. Is this, number one, is this really how fires have always been fought? No. And we don't have to go back to Ben Franklin's day to find a difference. We only have to go to IFSTA Essentials 200 or IFSTA Essentials number 1 in 1977, and they had this wonderful table. I appreciate it may be a little hard to see, but basically it broke fire up into 3 groups: beginning fire, flame production, and smoldering fire. They talk about what the oxygen concentration is, what the toxic gas concentration is, and how that's going to affect the fire condition. Then they say, what do you need to do to put it out? Well, you got this little tiny fire, go in and put it out, direct application. How are you going to do that? You're going to make entrance, locate the fire, apply extinguishing agent to the base of the fire. Oh yeah, protect yourself with breathing equipment if you got it. Then ventilate if needed. What about in this case? Full involvement. Got a room full of smoke, room full of flame. It says you want to reduce the temperature to 300 degrees or less before you go in. It says entrance might be difficult because of heat. Personal protection if needed. Again, what do they tell you to do? Locate the area of major involvement. Size up. Determine the point or points at which application is to be made. You're going to apply where the water where the fire is. Make an opening, if needed, as small as possible for application of water fog. Basically, make a little hole, stick the fog line in, and then they start talking about how to be careful if you're doing that because you got red ball gloves on, at best, or again, maybe the farm work gloves and they don't want you to get steamed. When you see that everything's cooled down, enter and extinguish the remaining fire. What about if you got a smoldering fire? No fire showing, the oxygen level's down, fuel-rich condition. Same thing. Reduce the temperature before you go in. Locate, same deal. So what we're talking about doing today is absolutely nothing new. It's just trying to get things in balance. What happened to this table? When did it go away? Went away in the next edition, in the 1980s. What was going on in the fire service in the 1980s? What new equipment was the fire service getting in most parts of the country? SCBAs and turnout gear. So basically a decision was made, we've got a limited time to train our firefighters, and if we train them to put their SCBA on and wear it religiously, they won't have to worry about what the toxic gases are. We could save that for hazmat class. And if we've got this turnout gear that will protect them from heat, we don't need to be saying things like entrance is difficult because of heat, because now you can just charge right in there and you won't feel the heat for a couple of minutes maybe. So what happened is the technology that you adopted started to drive your tactics. And unfortunately, in that time period, some knowledge of fire behavior was lost. So all we're trying to do is to give that back to you, to help you make better decisions on the fire ground. I'll give you an example. You can do things different ways. These tests were run in May, earlier this year, down in Spartanburg, South Carolina, under an AFG grant, run through the International Society of Fire Service Instructors. And again, you can see our partners there from South Carolina and Spartanburg. So here, we're going to do the traditional attack. We've got a garage fire going. And in many parts of the country, if you ask for the department's SOP on this type of event, they will tell you that what they're going to do is they're going to make entry into the front door, and this thermal imager is looking at the front door here. We're inside the house looking out toward the front door. The front door's still closed. They'll make entry and they'll do their search. They'll bring a line inside. They'll bring the line into the kitchen. They'll force the kitchen door. They'll apply water from the kitchen and push the fire out of the house. What's the thought process behind that? You don't want to push the fire in the house. That's been the concern. Well, remember, one of the few pieces of fire-rated structure in a house is this door and the wall between the house and the attached garage. Pretty much nothing else in your house has a fire rating. So let's see what happens. The officer's doing the size up. We have a firefighter going to the front door. He's going to open the front door. We'll see that open up. There we go. The front door is open. The kitchen is just off to the left-hand side here with the open doorway that empties to this hall that goes to the front door. We start to see some mixing, some air movement as they've started to open up a flow path here where hot gases can flow out the top, fresh air can come in the bottom of that door. We open the door. We've got a charge line down here. Within 10 seconds of opening the door, we're going to start to flow water, 150 gallons a minute straight stream. You can see the amount of thermal energy that's flowing into the house. The line's open, and we're going to start to see that it's going to have a very positive impact and put this fire out. Everybody can go out in the front yard, mop up the fire. It was a good day. Life's pretty good. The homeowner will call the insurance company, call the cleanup crew. They'll rebuild the kitchen, start doing some other work here in the hallway where they may have soot and smoke damage and fire damage. Let's look at the same kind of fire, but another approach. The firefighters in the previous case went into a structure. They were exposed to cancer-causing gases. They were exposed to heat, and they successfully put the fire out. In this case, we have the only difference in views is this thermal imager is looking at the door, this same kitchen door right here. In this case, we don't have a hose in the house. The officer's going to do the size up, and then he's going to direct his firefighters to make an attack literally from the curb, because you don't want to get too close to a car fire. Why? It's got a lot of projectiles in it, right? It's got hood struts, it's got bumper struts, all kinds of things that can shoot off at you. So give it a little bit of space. You don't need to get right on top of it. Your hose stream has a reach, and you want to use that to good purpose. So you can see we've got the fire building up pretty good. The officer's making his size up here. In the meantime, the crew's getting the line ready, waiting for that officer to tell them what's our plan of attack. Notice that the conditions in the kitchen aren't all that bad, right? As long as that door is closed. We saw in the previous video what happens when you open the door. The fire, under pressure, pushes its way into that kitchen and starts that kitchen on fire. All right, he's getting with his crew. And we're going to start flowing water from the curb. Again, straight stream, 150 gallons per minute. Get it up where the hot gases are, knock the gases out of play, the fire goes away. Done. They're going to move in, they're going to hit it some more. What's going on in the kitchen? Let's say the homeowner was making a pastrami sandwich for lunch, and they just got it in the bag when they realized that their garage was on fire. They ran outside with their cell phone, and they called the fire department. Well, in the interior attack case, the pastrami sandwich probably did not survive. What about in this case? Here it's only got to worry about surviving the mop-up crew, right? Very, very different. The firefighters here are not exposed to that thermal stress. The firefighters here are not exposed to as much cancer-causing smoke, perhaps. Another crew can be forcing the door, doing a search, doing whatever right now without the worry or concern about where's the flow path, am I going to have a ventilation-induced flashover in this structure? And it can be done very fast. So ventilation, another big part of your business, vent to cool. No one is saying today don't ventilate. We're talking about coordinated tactics, making sure that when you do ventilate, it's an appropriate time. When you do ventilate, you've got a line ready to deal with the fire. Coordination is a big deal. Well, a lot of times people say, coordinate with what? We hear that term all the time. So again, we're going to try to give you some examples. And is vertical ventilation better than horizontal ventilation? Back in the day, they say, well, horizontal ventilation, you've got to be careful about when you do that. We understand that. But vertical ventilation, you can do that anytime. Is vertical ventilation really ever just vertical ventilation? It's a combination of horizontal for the inlet air and vertical for the exit air. Anybody have a wood stove at home? Anybody got a good barbecue grill? How's that work? Got to let some inlet air in for combustion, and then you vent to let the products of combustion out. And if you crank up the inlet air, what happens to the fires? It gets smaller or bigger? It gets bigger. You guys know any blacksmiths? We're out here in horse country. We passed a horse farm or something. How do the blacksmiths operate their forge if they want to get a hotter fire going? Crank some more air into it, right? So here's where the fire dynamics really starts to come into play, right? Because this is where the chemistry and the heat transfer, the mechanical engineering, all that kind of stuff kind of comes into how do we mix these chemicals and the oxygen together to control the fire, either to make it bigger or to make it smaller. Well, keep in mind that fire is a gas phase reaction. Again, you learned that in Firefighter 1. They said it in a little different way. They said solids don't burn and liquids don't burn. And what they meant is the fuel has to be in a gaseous form to mix with the oxygen that's already in a gaseous form in air in order to have this chemical reaction. Then we just need the heat to get it going. And if we can sustain that chemical reaction, uninhibited chemical reactions, that's the added part for the fire tetrahedron, we can keep the flaming combustion going. This should be very familiar to you. This has been taught for decades, that a fire is going to, the phases of fire, we're going to have ignition, it's going to go through a growth stage, it's going to be fully developed, and then as the fuel's depleted, it's going to go into decay. This is sort of a new look at the fire, because this fire only describes a fuel-controlled fire. So if you put pallets out in the parking lot, it's going to behave like that. You put an appropriate amount of logs in your fireplace, it's going to behave like that. We have a small fire in this room and keep it small, it's going to behave like that, controlled by the fuel. If we have a fuel-rich condition, this is what's going to happen. We're going to have ignition, we're going to have growth, and then the fire is going to overrun the amount of oxygen that's available to it for combustion. And as a result, the heat release rate of the fire and the temperature of the fire is going to start to go down, and it can go down pretty rapidly. And then there's going to be a change in ventilation. That change in ventilation could be as simple as the officer opening the front door, or as a state trooper opening the front door and leaving it open. And now you're going to start this ramp. And this ramp could take 30 seconds to flash over, could take 80 seconds, could take 3 minutes, depends on the size of the house and how depleted the fire got before somebody gave it oxygen. But many firefighters have experienced this rapid change. Unfortunately, this year alone, we've heard it a couple of times from chiefs of department when they're having their post-line of duty death interview. And they're saying, well, the 2 firefighters that died in our department, you know, that was the fastest fire growth I've ever seen in my life. Our firefighters were okay. The 2 firefighters were upstairs doing their job, and then all of a sudden there was a rapid change. This is what's causing that rapid change. So the first thing you have to recognize is smoke is fuel. And here's a demonstration you can do back in the firehouse. Take a candle, blow it out, bring the match to the fuel gases. Notice the match did not go to the wick. It went to the fuel gases and lit the fire. Then take a spoon, run it through the candle, and what is that flame really? It's carbon. It's fuel. And if we slow it down by putting this cold object in there, we'll see that soot condenses on that object, right? So the flame is really all these carbon particles that are under such a high state of energy that they're beating and banging against each other so fast that they're glowing and emitting heat and light. That's what the flame is. We slow it down, we see it's nothing but little soot particles. You got to recognize that the fuels today are different. We talked about the difference between natural fuels and synthetic fuels, fuels that are made from petroleum products. Well, here's another great demonstration you can do. Take a sliver of wood, light it with the candle. What do you notice about it? Pretty small flame, pretty clean burning, and if you're holding it with your fingers, you'll be able to hold it for a couple of minutes because the flame spread's going to be pretty slow. Now let's take a piece of expanded polystyrene. And they might say, Dan, where on earth am I going to get a piece of expanded polystyrene? Now, how many people have foam coffee cups in their firehouse? That's expanded polystyrene. Take a sliver of that foam coffee cup, and I suggest you have a glass of water or something, be ready to drop it pretty quick because you'll see that it burns a little bit differently. You'll see that we have excess fuel in the form of this visible soot that we can see. That's excess fuel that didn't burn, and the flame spreads a lot faster. Anybody ever operate an acetylene torch? Does that look similar to the two sets of pictures I just showed you? In one case, if you turn on the acetylene torch and you don't turn on any additional oxygen, you're going to get this weak, very fuel-rich flame, and a lot of the excess energy, the potential energy, this excess fuel is being given off in the form of soot, big, long-chain soot particles. Because what this particular fuel needs is more oxygen to burn efficiently. In order to get as much energy out of it as you possibly can, in order to get it to burn clean, it needs more oxygen. So if we pre-mix oxygen with the acetylene, now you see we have a lot more energy from the same gas flow, and you see how clean it burns. So the key point here to remember is with no oxygen, you can't have any heat. You've got to have that mix of the gaseous fuel and the oxygen to get heat. One thing that was discovered at NIST in the early 80s was that regardless of the kind of fuel you're burning, for every kilogram of oxygen that you burn in a fire, you're going to generate 13 megajoules of heat. Don't worry about the numbers. The key thing is no oxygen, no heat. So here we have a fairly typical living room. 12 feet by 12 feet. It's got an open doorway. Has a nice over-dry Christmas tree in it. We've got a sofa made of with polyurethane foam seat cushions and polyester batting and polyester covering. We've got a chair over here. We've got an open door, so we're allowing air to come in and supply the fire. There's the fire triangle right there. It's where the fuel gases mix with the oxygen, they have enough heat, and the flames are burning. Are the flames burning against the wall? No, they're burning at the interface of the gases and the oxygen where they're mixing. Now we see due to radiant heat transfer, we're pyrolyzing the sofa. What does that mean? That means that we're taking the solid material and we're breaking it down just by heating it and turning it into gaseous fuel. That white vapor you see going up into the hot gas layer is fuel. Again, once we get the right concentration of fuel and heat and oxygen, that hot gas layer is going to start to burn. Notice how slow the air is coming in and mixing. As we transition to rollover and transition into flashover, you're going to see that this mixing gets very violent. It looks like we have wind-driven flames on the floor, and then it goes dark. Did the temperature cool off in here? It might have dropped from around 1,800 degrees to 1,500 degrees when it went dark. This is what people refer to as black fire. The gases are hot enough to kill you. They're almost as equally hot as flames. However, there's not enough oxygen there to support the flaming combustion. Where's the fire now in this structure? If I had time, I'd show you another video of this, and you'd see that we've got 8 to 10 foot flames out the front door. So I've been throwing some terminology around, and we're moving kind of quick today, but the key point here is heat release rate, energy that's given off by the fire. That is the hazard for you. It's not necessarily temperature. Temperature is the end result. When you hear people about fires being hotter today, that means they're giving off more energy and giving it off faster. They have a higher heat release rate. So let's go back to the candle again. If I've got a single candle and I put a thermometer or a thermocouple in the candle, I might get a temperature value of, say, 1,400 degrees. And if I put it under a calorimeter and measure the heat release rate, it's going to tell me it's about 80 watts. If I have 10 candles and I put them all together, and I stick that thermometer in the flame of all 10 candles together, is the temperature going to be 10 times higher? No, temperature is going to be about the same. The heat release rate, the energy that's being put off, is going to be 10 times higher. Same kind of thing if I had 2 pallets on that side of the stage burning, or I had 20 pallets stacked up over here on fire. Which one is the bigger fire hazard? The 20 pallets, right? The flame temperature from burning wood pallets is going to be about the same, but the heat release rate, the amount of energy given off per time, is going to be very, very different. We're going to do a couple examples, then we'll turn you loose for our break. Here we have a room. It's about 12 feet wide, 9 feet deep or so, and 10 feet tall. I've got a 42-pound chair there in the corner that we lit with a small book of matches. I've got some turnout gear samples here on the wall opposite that, and they're about 3 feet or so above the floor. And we've got a thermal pane window here, dual pane that's closed, and we have a door that's closed. As the fire's burning, we have the thermal plume coming up. As we talked about before, the fire's a pump, and it's building up this hot gas layer, and the hot gas layer is expanding, and it increases the pressure, and because it's higher pressure than outside, smoke pushes out from around the doorway, right? Higher pressure goes to low pressure all the time, until we get to a point where the hot gas layers come down. It's consumed most of the oxygen in the structure, and the temperature and the energy starting to drop until we open the door. Now that fire was still in an incipient stage when it started to darken down, still limited to that chair. So opening the door, creating that ventilation, works perfectly. This is exactly what you'd hope to find. You open the door, the hot gases go out the top, the fresh air is going in the bottom, and look, you've got visibility back. The heat has lifted. This is fantastic. This is exactly what ventilation is supposed to do. But if you open the door and you don't have the hose line ready to go in, you don't coordinate your tactics, you'll see that just the energy coming off this 42-pound chair is going to overrun that vent. The energy is going to increase. We're going to start to have rollover. Notice that it clears the interior pane but doesn't break the exterior pane. Notice where the flame is moving. It's moving toward the low pressure vent. It's moving toward the source of oxygen. And now in this case, we're going to shut it down with a sprinkler before it goes into full blast mode for the flashover, because we're trying to protect the turnout gear here to see how bad it was damaged. So what's that look like? And again, I'm trying to get a lot of the graphs out of the way before I let you go to coffee and go to the bathrooms, but please come back. So I'm just telling you just a few. Temperature's going up. It's peaking at around 500 degrees at the ceiling. Down around the floor, we're sitting at about 150, 200 degrees or so. You saw it darken down. The temperatures in that room dropped. Then we opened the door, and notice how it's separated. The temperatures on the ceiling and down to about 3 feet above the floor increased to 400 degrees to 500 degrees again, and the ones from 3 feet above the floor and down remained at ambient temperature that day, which was about 100 degrees outside. That's perfect. That's that ideal convection case that I was talking about. Hot gas overhead, fresh air coming in down low. But you don't have a lot of time, because then once it starts to transition to rollover, look what happens. Right? The temperatures from the ceiling down to the floor are starting to skyrocket. And notice that they're getting way above that normal or ordinary range. They're getting way above 400 degrees Fahrenheit and just ramping right up. So it's becoming untenable for a firefighter in there. What about heat flux? Well, we have total heat flux, which is the convection and the radiation added together. And we see that here, we hit about 50 kilowatts per meter squared. And then we just have the radiant heat flux itself, just the light energy, which was about 10 kilowatts per meter squared. So you're in there, you're in your turnout gear. You may be sitting in the room waiting for Joe to bring the hose line to you, or you got in there and you said, you know what, this is just a can job. Go have the probie bring us a can real quick. And you're sitting in there and you're not paying a lot of attention, and bang, it goes from tenable conditions in your turnout gear, 5 kilowatts per meter squared, to untenable conditions of 50 kilowatts per meter squared. And how long did it take to do that? Well, each one of these marks is 20 seconds. How many of you have heard that it's said that fires double in size every minute? It's nonsense. What's the ventilation? What's the fuel? That's what's controlling the fire. This fire went from 5 kilowatts per meter squared. The heat intensity increased by 10 times in about 20 seconds. That's this rapid change that people talk about when there's an injury or a line of duty death. What's going on with your turnout gear? The outside of the gear is sitting below 200 degrees. The inside of the gear is lower than that. And then we have rollover, and you see how the outside temperature of the gear gets up to almost 1,000 degrees very quickly, and the interior becomes untenable as well. That's your area of safety, that little gap right there. Let's look at another case, one last case I promised before we go on break. Same kind of room, same 42-pound chairs that we're lighting on fire. In this case, I'm leaving the door open and I've got one window open. So show of hands before we go on break. Is this going to go to flashover faster or slower than the last time? Who says faster? Put your hands up. All right. Who says slower? Lesser number. And then we still have a bunch of agnostics in here that aren't willing to commit. Dan's been telling you that you live in a fuel-rich environment, and if you give it more air, it's going to transition faster. We're leaving the door open to give it more air. Let's see what happens. It's playing in real time now. We're going to watch it roll over again. Watch where the flames are. Watch where they're moving. They're going toward the open door, the low-pressure vent. We call this the neutral plane. High-pressure hot gas coming out the top of the door, cool, fresh air being entrained or being drawn into the door. So we're transitioning to flashover a little bit faster. Pyrolyzing the carpeting, burning the carpeting. We got gases burning. We've got a unidirectional vent or a pure exhaust vent coming out of that window. And notice that this doorway is still a bidirectional vent. Hot gas out the top, fresh air in down low. That's supplying the combustion for that fire. What you'll notice, why is this only an exhaust vent? Because the neutral plane is down here. So that's basically in the exhaust layer, hot gas layer. So if you're doing a size up and you see a window that's top to bottom venting out smoke and fire, that's telling you that it's getting air from somewhere else if the door's not conveniently located next to it. You need to go find out where it's getting air, see if you can shut that down. Easy knockdown. Fire can't really breathe. It's so fuel rich. It's struggling to make flames here. And again, that room looked pretty empty. 2 42-pound chairs and some carpeting on the floor. Here's the temperature. You see we don't have that nice separation like we did before. It just keeps ramping up till it gets to flashover. Burning above 1100 degrees Fahrenheit, floor to ceiling. There's our knock on it with the fire hose. Bang, dropping it down to 200 degrees real quick. Heat flux, we let it go to transition to flashover. We got up to 70 kilowatts per meter squared total, which is the convective and radiative added together. Radiation only about 30 kilowatts per meter squared. In this case, the turnout gear was destroyed. And again, you see how rapidly that transition was made. Let's go ahead and take about a 15-minute break, maybe come back at 10 of, and we'll get into flow paths and exterior knockdown.